In this video, we're going to determine whether certain series are convergent or divergent. With the problems on this worksheet, we'll restrict ourselves to the test for divergence, the integral test, and convergence of p-series. Recall that a p-series is a series of this form here, and as we discussed in class, a p-series will be convergent if p is greater than 1, and divergent if p is less than or equal to 1. Looking at part A, the sum n equals 1 to infinity of n to the negative 7. We can rewrite this as the sum n equals 1 to infinity of 1 over n to the 7th. Here we have a p-series with p equal to 7, which is greater than 1, and this implies that our series is convergent. Part B, the sum n equals 1 to infinity of 1 over the 4th root of n. This one can be rewritten as 1 over n to the 1/4 power. Again, this is a p-series with p equal 1/4, which is less than or equal to 1, which implies that the series is divergent. Part C, the sum n equals 1 to infinity of 2 over 4n plus 3. Unfortunately, we can't rewrite this as a p-series. There's no way to rewrite 4n plus 3 as n to some power. So we're going to have to try something else. We could first try the test for divergence pretty quickly. If we have the series n equals 1 to infinity of a sub n, we look at the limit of the sequence of terms as n goes to infinity. If this limit does not exist, or if it does not equal 0, then the series is divergent. If we get any other result from this limit, then the test for convergence is inconclusive. We can never conclude that a series is convergent using the test for divergence. So if we were to take the limit as n approaches infinity of 1 over 4n plus 3, this limit would equal 0. And the test for divergence is inconclusive. We have to do something else. Now let's recall the integral test. In order to use the integral test, we have to first make sure that the function that corresponds with the terms of our series on the interval 1 to infinity is continuous, positive, and decreasing on 1 to infinity. From there, we'll determine whether the integral from 1 to infinity of this function is convergent or not. If this integral is convergent, then the series will be convergent. If this integral is divergent, then the series also will be divergent. So in this case, we'll consider the function f of x is equal to 2 over 4x plus 3. First of all, notice that it is continuous, positive, and decreasing on 1 to infinity. We can easily see this is decreasing by comparing f of x with f of x plus 1. Since the denominator on the right is larger, that makes that fraction on the right smaller. This means we can apply the integral test. So now we determine whether this integral is convergent or divergent. As t goes to infinity, ln of 4t plus 3 goes to infinity. So our improper integral is divergent. Therefore, the series is also divergent by the integral test. Part D, the sum n equals 1 to infinity of n minus 1 quantity to the third over n squared times the cube root of n. First, let's go ahead and rewrite this in a simpler form, and then maybe try the test for divergence. So here we've cubed the numerator, and we've rewritten the cube root of n as n to the 1/3 power. Now let's see what happens when we take the limit as n goes to infinity of the terms of this series. We can rewrite this limit like this by breaking it up into 4 separate fractions. Letting n go to infinity, the first term goes to infinity, and each of the last 3 terms go to 0. Therefore, our original series diverges by the test for divergence. Part E, the sum n equals 1 to infinity of n times e to the negative n. If we were to try the test for divergence here, we would take this limit. We notice that both the top and the bottom are going to infinity. So if we tried L'Hopital's rule, we would have something like this. Letting n go to infinity now, we get 0. So the test for divergence is inconclusive. We're going to have to try something else. So let's look at the function f of x equals x e to the negative x. And notice that it is continuous and positive on 1 to infinity. In order to use the integral test, we also need f to be decreasing. So let's go ahead and look at f prime using the product rule. The denominator is always positive, and the numerator will be negative for x greater than 1. This shows that f is indeed decreasing. So now we apply the integral test. We can integrate this using integration by parts. The tabular method is quickest. You can pause the video and do that on your own. With this limit, we notice that the numerator is going to negative infinity and the denominator is going to infinity. So we can apply L'Hopital's. This limit, as t goes to infinity, is going to 0. Now we take that first limit, and again we get 0. So we just have 2 over e. In other words, our improper integral converges. Therefore, the series also converges by the integral test. Part F, 1/3 plus 1/7 plus 1 over 11 plus 1 over 15. First, we'll rewrite this using sigma notation. We notice that in the denominator, we start with 3, and to that, we add 4 to get each subsequent term. Of course, for the first term, we don't want to add anything, so here we're going to put n minus 1. You can pause the video and plug in values for n to double check that this works. Now we can simplify this so that we have the series 4n minus 1. We can do a quick test for divergence in our heads by taking the limit as n goes to infinity and realizing that gives us 0. So the test for divergence is inconclusive. So let's see if we can apply the integral test. If we consider the function 1 over 4x minus 1, it's continuous on the interval 1 to infinity. The only discontinuity is at 1/4. It's positive, and it's decreasing on 1 to infinity. We know it's decreasing because as we pick larger and larger values of x, the denominator continues to get bigger and bigger while the numerator stays constant. So the integral test applies. Now we'll take a look at the improper integral from 1 to infinity of 1 over 4x minus 1 dx. A u substitution will help us integrate this. You can pause the video and do that on your own. As we let t go to infinity, this term goes to infinity. So our improper integral is divergent. Therefore, by the integral test, our series diverges as well. Part G, the sum n equals 1 to infinity of n over 1 plus n squared. Here again, we can first try the test for divergence. The limit as n goes to infinity of the terms of our sequence goes to 0, so the test for divergence is inconclusive. We have to try something else. We'll consider the function x over 1 plus x squared. We notice it is continuous, positive, on 1 to infinity. Let's take a look at the derivative and determine whether it's decreasing. Using the quotient rule, so the derivative is less than 0 for x greater than 1. So f is decreasing on the interval 1 to infinity. And now we can apply the integral test. You can go ahead and pause the video and integrate this using u substitution. The limit of the first term goes to infinity, so our improper integral diverges. Therefore, our series diverges, by the integral test. So as you proceed with the rest of the problems on this worksheet, realize that every problem will utilize either the test for divergence, the integral test, or you'll have just a simple p-series.